this last section, we're going to talk about the multiplication rule, complements, and conditional probability. So, independent versus dependent events. So, two events are independent if the occurrence of one event does not occur the probability of another event. For example, if I toss a coin and roll a dice, whatever I toss on that coin has no effect on that dice. So those two events are independent. If two events are not independent, we say they are dependent. So if I was to pick a card from a deck and draw a heart, okay, and pick a card from a deck and I don't replace that first card and I draw another card, right? What I get that second time depends on what I have in my hand already because we didn't replace the card. This is an example of sampling without replacement, which I'm going to talk about further on in this section. So if two events are independent and the outcome of one event does not affect the other event, then we multiply their probabilities together. So this is a principle that can be extended to multiple numbers of independent events, just like the additive principle. So suppose you get 3 fair coins. What's the probability of getting 3 tails? Well, that's going to be the probability of getting 1 tail times the probability of getting another tail times the probability of getting another tail, which is 1/8. Suppose you roll a die and flip a coin. What's the probability of getting a 3 and a tails? So if I'm rolling a dice, the probability of getting a 3 is 1 out of 6. And if I'm flipping a coin, it's a half. So the probability that I would get a 3 and a tails is going to be 1/12. So those are independent events. When events are dependent, the outcome of one event is affected by the outcome of the other event. So the probability of A and B is the probability of A times the probability of B given that A already occurred. And we're going to talk about how to calculate that in the next slide. No, we're not. I'm going to do it right here. So this is called conditional probability. And the probability of B given A is the probability of them both occurring divided by the probability of A. So let's go ahead and figure this out. So a batch of 15 memory cards contains defective cards. Okay? What's the probability of getting a defective card on both the first and second selection without replacement? So I have a 5 out of 15 chance of getting a memory card on the second chance, but I didn't put my card back in. So now there's only 4 out of 14 left. So I would have 15 times 14, sorry guys. I would have 20 out of 210, which is 20 divided by 210 is 0.095 or 9.5%. So with replacement is when you put the object back into your sample. Without replacement is when you don't put it back in. So let's compare those. So you have a bag that contains 10 red, 3 white, and 2 green marbles. You're going to pick 2 marbles from the bag, and you do not replace the first marble. And you do, in this one, you do replace the first marble before you pick the second marble. And I want to know what's the probability that they're both red. So I've got 15 total. So the probability of getting 2 reds with replacement is 10 out of 15 times 10 out of 15. So that's 100 out of 225. Now what about without replacement? Well, if I draw a red marble on my first try, then my next try, that means there's 1 less red marble for me, and there's 1 less marble in the bag total. So I would have 90 over 210. So let's calculate what these probabilities would be in decimal form so you can see them a little more closely. So this would have a 0.43 probability of drawing 2 reds, whereas otherwise, yeah, that was a 2, sorry. 100 divided by 225. Whereas otherwise, I would have a 0.44 probability, which is bigger, right? Just a little bit, but it is bigger. So if a small sample is drawn from a large population, we can treat the events as independent, even though strictly speaking, they are not independent. So for example, if we were to choose 2 female high school students from high schools in Missouri, what's the probability their name is Hillary? Okay, so let's assume that the female, probability of a female having the name Hillary is 1 out of 1,000. So we can multiply these together and treat them individually. And treat them as independent events. Another example of this is if we know 10% of the world's population is left-handed, what's the probability that waiting in line in the library, the next 3 who enter are left-handed? So even though the size of the population is not small, if we chose a sample size of 3 and compared it to the population of the world, these events are theoretically dependent, but we'll treat them as independent, and we can compute the probability that 3 people in a row are left-handed.